Calculus Video 69, Riemann sums and the fundamental theorem of calculus. So a couple of really big topics here with Riemann sums and the fundamental theorem of calculus. I'm going to pull in what we learned last time from the previous video. The very end, we talked about having the right-hand method, doing the area under the curve as an approximate using the sum formula, the sum notation or the sigma notation. We found out for the right hand, the area under the curve is approximately equal to the sum from I equals 1 to n, where n is the number of rectangles. N equals number of rectangles. Of delta x, where delta x is the width of the rectangle, times the height of the rectangle, which can be given for the right-hand method, f of a plus delta x times I, where a is the starting point, right? That's on the interval a to b. And we can get the right-hand method using this formula here. What I want to do today is to generalize this formula a little bit more to turn it into what's called a Riemann sum, and then introduce the fundamental theorem of calculus. Okay, so big video here. Let's start with a picture. So in the area under the curve, I picked drawn a function f, and I have my interval from a to b, and I've chosen to use 4 rectangles just because it's easy drawing. Okay, and here I have the right-hand method. Notice that on the height of every rectangle is being given by the point on the right side, the rightmost point of every rectangle. Okay, I need to generalize this a little bit more. Okay, because what I said before was that it doesn't really matter whether you're using the right-hand method or the left-hand method or the midpoint method, or there's even like a trapezoidal method. It doesn't really matter, because what's going to happen is, to get the exact area under the curve, we're going to let the number of rectangles go to infinity, which makes the width of each rectangle approach 0. And so the left-hand side and the right-hand side squish together anyway. Right? And so it doesn't really matter here in a little bit whether I use the left-hand or right-hand side. So I would want to generalize this, where I'm not just saying the right-hand method is this, or the left-hand method is this, or the midpoint method is this. What I want to do now is replace this complicated f of a plus delta xi, kind of a complicated thing, with a more basic thing. And so instead of that, what I want to think about is, I want to take the height of the rectangle, not from the right-hand side with the right-hand method. I want to take the height of each rectangle from any point C that's in the width of the rectangle. For example, it doesn't matter where at. I'm gonna just pick some point C. I'm going to call this C1 because it's some point C in my first rectangle. It may be the middle, it may be the right, it might be the left, it may just be some point in there. And so I'm going to pick the height of that rectangle coming from C, C1 in this case. It's going to look something like that. Oh, too much. On the height of the second rectangle, I'm going to pick some other C value. All right? As long as the C is in the second rectangle width, maybe it's way over here in the left-hand side, C2. It doesn't matter as long as it's somewhere in there. I'm going to pick the height of the second rectangle as f of C2. Looks like about right there. Right? So the height of the first rectangle occurred at f of C1. The height of the second rectangle is f of C2, and we're just going along, we're just picking the heights of the rectangles at some point C within each one. Maybe the C3 is way over here. And so now the height of the third rectangle occurs from right here, which is f of C3. And then fourth rectangle, maybe it's kind of right in the middle on the fourth, C4. And so the height here would be kind of right in this region there. Let's see if I can make those a little bit better. Something like that, right? And then F of C4. So what we're doing here is we're no longer going left hand, right hand, midpoint. We're just saying choose the height of each rectangle given some point C in that width of the rectangle, in that particular rectangle. So we're making it more general. If we do that, instead of now just right hand, now we can say this. We can say that the area under the curve is approximately equal to the sum from I equals 1 to n, that part doesn't change, of delta x, that part didn't change, but instead of f of a plus delta x times I, we can just do f of ci, right? So that's c1, f of c1, f of c2, f of c3, f of c4. That makes a more generalized version of the summation where we're not just doing right hand, left hand, or midpoint, but as long as any point C in each subinterval, we call it. Okay, that's our first step of generalization. So that's a little bit of a simpler form. The second thing we want to do is we want to say, and this goes against what I said in the previous videos of, to make my life easier, I kept all rectangle widths to be the same. They were all delta x, right? This was delta x. That's the width of that rectangle. Every rectangle, right, had a width of delta x. That's not really the most general way I could write this. It could be that I could break this up into rectangles where the first rectangle is really wide and the second rectangle is really narrow and the third rectangle is kind of normal and the fourth rectangle is also narrow. Right? I could have instead, would my function look like kind of like this, kind of look like this, f from a to b, from about a to b, just trying to draw something similar. I could have instead broken this up where my first rectangle is really wide, my second rectangle is really narrow, my third rectangle kind of normalish, and my fourth rectangle maybe kind of like this. In other words, the widths of each rectangle do not have to be the same. It was easier for my calculations before, but it wasn't the more general form. The more general form is you can as long as you have 4 rectangles, it doesn't really matter how wide each one of them is. Again, with the thought in your back of your mind, we're going to have infinitely many rectangles. We're going to approach infinitely many rectangles. So the fact that one is wider than the other really shouldn't matter because we're going to have infinitely many of them. Okay, so what that means is I can't just have delta x anymore, because delta x means we were saying that every rectangle has the same width of delta x. Instead, each rectangle has its own width. This first rectangle, we'll call it delta x of the first rectangle, delta x1. The second rectangle will have a width delta x2. The third rectangle, delta x3, because it could be different sizes, and finally delta x4, right? Where the delta x is the width of each rectangle. And so no longer can I just do delta x. To allow the rectangles to have different sizes, we now get this. the area under the curve is approximately equal to the sum I equals 1 to n of not just delta x, but delta x I. Delta x I. Meaning that this is the first delta x, the second delta x, the third delta x times f of ci. Now what we've done is we've generalized it to allow the height to come from any point within the subinterval and the width to be different for different rectangles. And when we've made these two generalizations, we get this thing, this sum, and this sum is called a Riemann sum. That is considered to be a Riemann sum. And that is an approximation of the area under the curve. The more general form of an approximation of the area under the curve. Not choosing left hand, right hand, or delta x's all being the same. Okay? Now that we have Riemann sums, let's take the next big leap. And the next big leap goes from an approximation of the area under the curve to an exact area under the curve. And the only thing we really have to do, and we'll kind of do this in two steps, but the first main thing is, instead of having 4 rectangles, have 8, the better approximation. Instead of 8, have 16. Instead of 16, have 64. Have 6,400 rectangles. Have 1,000,000 rectangles. The more rectangles you have, the more accurate it becomes, until we get the exact area under the curve by having an infinite number of rectangles. Or, more accurately, letting the number of rectangles approach infinity. Okay. Exact area under the curve. And we're going to make an adjustment to this in just a minute, but let's first think about it from this form. The exact area under the curve is area is equal to the limit as n, this is the number of rectangles n, goes to infinity, of the sum I equals 1 to n, of delta xi times f of ci. That is the exact area under the curve. That's great. We like that. One slight problem. This is technically how this is how I think about the area under the curve. The exact area is I have all these rectangles, right, and I let the number of rectangles go to infinity. Which, by the way, remember that delta x is equal to b minus a over n if they're all the same size. If n is going to infinity, then b minus a, which is a number, divided by infinity, we get delta x goes to 0. So if n goes to infinity, delta x goes to 0 as long as they are the same size. As long as this is for when delta x are the same size. But if we allow delta x to be different sizes, we could run into a problem. And here's the problem we could run into. It's kind of like it's a technicality, but we want to make sure we take care of it. Let's say we have that same sort of function here, and that's f, and I'm going from a to b, and I'm having infinitely many number of rectangles, but my first rectangle is here, and it stays that big. And even though I have infinitely many rectangles from there on, right, picture lots and lots and lots and lots of rectangles, and they get smaller and smaller and smaller and smaller and smaller and smaller, right? and then it's more and more accurate over here. But if my one rectangle stays big, even though I may have infinitely many rectangles here, I'm spelled right, infinitely many rectangles here. In other words, n is going to infinity. And so the area from here, from past that first rectangle becomes exact. I still have error if my first rectangle never got smaller, right? If I've got this one rectangle, and it doesn't have to be one, it could be 2 or 3 or 15, but if you have one rectangle that doesn't actually get smaller, that doesn't get, the width does not go to 0, so for this particular one, the delta x does not go to 0, that creates error, which means I won't have an exact area under the curve, even though the number of rectangles went to infinity. So we have to take care of this, and so we come up with one thing where we break up a region into rectangles, we call that a partition. A partition is separating a region into, or separating an interval is probably a better. Separating an interval, A to B in this case, into subintervals, smaller intervals. That separation, how we separate that interval A to B into subintervals is called a partition. If the way we partition this goes from A to B, and even though there's infinitely many, if from A to, say, I don't know, call this D, if that never changes, if that width never goes to 0, we are going to still encounter area in getting the area under the curve. Sorry, we're going to encounter error in getting the area under the curve. So it's not enough just to say we have infinitely many rectangles. We have to say that every rectangle, the width of every rectangle must go to 0. All right. So in a partition like this, we are going to denote double bar delta x. So this is one of the partitions, and let's call this the largest. The largest subinterval width. All right, we're going to say this is the largest subinterval width. So picture kind of like this first one. That's like our biggest one. And what we're going to say is, instead of saying the number of rectangles go to 0, because it doesn't force every rectangle width to go to 0, we're going to say the largest subinterval width goes to 0. And if the largest subinterval width goes to 0, that means, since it's the biggest, that all subintervals must also go to 0. Right? So saying this, saying that the limit as the largest subinterval goes to 0 means that every delta xi goes to 0. If the largest one goes to 0, then they all go to 0. And that's what we're really wanting. In order to do this, we have to have infinitely many rectangles for them to approach 0. For the largest and for all of them to approach 0. So in my mind, I'm still thinking I need infinitely many rectangles, but this kind of makes sure that we're keeping track of the situation where I have infinitely many rectangles, but yet the largest one doesn't go to 0. So we're forcing the largest one to go to 0. So what we do is, just for that one particular case, we're going to rewrite this. The exact area under the curve, not as the limit as n goes to infinity, even though in my mind that's really what I'm thinking. I'm thinking infinitely many rectangles. we get this. The exact area under the curve area is equal to the limit as the largest subinterval goes, lost my fault here. I forgot my delta. Sorry about that. Delta x, the largest subinterval. And in this case, I forgot my x. Kind of lost each part of that there. The delta x goes to 0. The largest subinterval goes to 0. And again, when you see that, you're thinking, okay, in order for that to happen, the n must go to infinity. It must have infinitely many of them. Of the sum, I equals 1 to n, of delta xi times f of ci. And we have found, finally, the most generalized form of finding the exact area under the curve. It's the limit as the largest subinterval goes to 0 of the sum I equals 1 to n of delta xi times f of ci. F of ci. All right, very good. Take that and let's say, how do you solve it? What if I was to ask you, here's a function, tell me the exact area under the curve? Think about how hard that is. Think about what we'll have to do. We have to partition it, and even if we say, okay, I don't want to mess with my delta x's being different sizes, I want them all to be the same size, I still have to let the number of them go to infinity and then add up the area of each one infinitely many times, right? In order to find the exact area, I would have to do the sum I equals 1 to n, even if I let delta x be just delta x, where they're all the same size and not different sized, and in that case I can go back to the limit as n goes to infinity. Since they're all the same size, I don't have a largest per se. Times f of ci. I have to do, okay, what happens when I is 1? Well, when I is 1, then I get delta x, whatever that happens to be, times the height at f of c1. And then I have delta x times the height at f of c2. And how many times do I have to do this? Infinitely many? And then I have to add them all up? That's not going to work. I can't do that infinitely many. I don't live that long. So how do you find the exact area under the curve? What comes to save us is what's called the fundamental theorem of calculus. If you hear fundamental theorem, that is a very important theorem. In our case, it is saving us from having to add infinitely many things together. Okay? The fundamental theorem of calculus says this. The area under the curve of the function on the interval AB is equal to, we'll do the most generalized form, the limit as the largest partition, the largest subinterval goes to 0, of the sum I equals 1 to n of delta xi times f of ci, which is, this is all we found so far. This is not new. Here's the new part. Is equal to the integral from a to b. Notice the bounds here become bounds on our integral of our function. So f of ci becomes f of x, and delta xi, as delta x goes to 0, right, we get dx, right, dx being a very, very, very small change in delta x, we get dx. Dx is notation for delta x going to 0. That's the fundamental theorem of calculus. Well, That's actually not the fundamental theorem of calculus. The fundamental theorem of calculus is the very next part, which says this is equal to capital F. Now, in the notation here, I have lowercase f. When I write capital F is the antiderivative of lowercase f. It's capital F evaluated at the upper bound b minus capital F, the antiderivative, evaluated at lower bound a. That is the fundamental theorem of calculus. We can use integration to find the area under the curve. I want to put like 5 exclamations here. That is super important and helpful. Let's try it. Example. Maybe we should here, big star somewhere, right? Fundamental theorem of calculus. Earlier we had this. This is a previous video. We had f of x is equal to 2x squared minus x on the interval from 1 to 5. No longer do I need to tell you how many rectangles. We're letting the number of rectangles go to infinity in order to find the exact area under the curve. But we're not going to use this Reimann sum as the partition goes to 0, as the subinterval goes to 0. We're going to use this second part. We're going to use that this is equal to this, which is also equal to capital F of b minus capital F of a. That the sum is equal to the integral from a to b of the function dx, which is equal to the capital F, the antiderivative evaluated at b, minus the antiderivative f evaluated at a. In other words, area under that curve, right? So the picture there, if you remember, we had this parabola, looks like that. That's not a great picture. From 1 to 5. We're looking at the area under this curve. The exact area is equal to the integral with bounds 1 to 5 of the function 2x squared minus x dx. And what we're going to do is we're going to use our knowledge of antiderivatives to take the antiderivative of that function. That would be 2x to the power of 3 now, divided by 3, minus x squared divided by 2, plus c. Hint, we're going to get rid of that c in just a second. Evaluated that, so the notation we use, we put a box here, and then we put the 1 to 5. That way we don't forget that we're evaluating this from 1 to 5. This 2x squared minus x, that's lowercase f of x. This 2/3 x cubed minus x squared over 2 plus c, that's capital F of x. That's the antiderivative. And what we're going to do is say the fundamental theorem of calculus says the area under the curve is equal to that capital F evaluated at 5 minus that capital F evaluated at 1. So I'm going to plug in 5 into all the x's and then subtract, plugging 1 in to all the x's of that antiderivative. It looks like this. 2/3 times 5 cubed minus 1/2 times 5 squared plus c. This is f of 5 minus 2/3 times 1 cubed minus 1/2 times 1 squared plus c. And that is capital F of 1, the antiderivative evaluated at 1. A little bit of math here. 5 cubed is 125 times 2, 250. That's 250 divided by 3 minus 5 squared 25, 25 over 2 plus c, minus 1 cubed is 1, 2/3 minus 1/2 plus c. Now, a couple things. Notice the constant here, c. I have a c minus a c. That will cancel out. That's always going to happen, that those constants will cancel out. So when we do this area under the curve, we actually never even write the c here because we know that that constant will cancel out. So from now on out, you will see me, I'm not writing the c when I'm doing area under the curve, when I have bounds on my integrals here. All right, so I'm not going to write those anymore. Then I do 250 divided by 3 minus 25 divided by 2. That's 70 and 5/6 minus 2/3 minus 1/2 minus 1/6 is 70 and 4/6 or 70 and 2/3. And that is the exact area under the curve. And we get that from the fundamental theorem of calculus. Okay, very good. Again, this video probably long enough for now. I'll stop it and then we'll kind of add a little bit more on the fundamental theorem of calculus in the next video.